In the series Odd Odds, Oddities, we take a look at single events that can occur in life. Today, we will ask what are the odds of a successful zombie outbreak? Hold on, this can happen in real life. Oh well, let's go with a red marker today. Nope, nope, nope. Gotcha. First, we'll have to determine what qualifies as a successful zombie outbreak. We'll determine that to be when the number of live zombies, Z, surpasses the number of live humans, H. In other words, when Z is greater than H. Therefore, at any point in time when Z is greater than H, a successful zombie outbreak has occurred. The initial conditions of zombie infection will be represented by Z0 and H0. Oftentimes, these values are 1, or the patient 0, and the world's current population, which of course could be substituted by a smaller subset, like a country or an isolated area. We do also have to define zombies. For our sake, they will be mindless, cannibalistic, undead former humans, so no zoonosis. Transmitted through infection, typically via bite. Indeed, since zombies can only be former humans, the maximum capacity of zombies before our threshold would be H0/2. If this number is ever reached by the zombies, we can assume the outbreak's successful. We can mark the threshold as Z1 and its counterpart during that time, H1. Therefore, when Z1 equals H1, the zombie outbreak can be deemed a success. We can also mark the final states as Z2 and H2. The final states occur when Z equals 0, H equals 0, or both Z and H are 0. Now we need to determine how Z0 becomes Z2 and how H0 becomes H2. For this, we'll use broad categories like the zombie death rate, human death rate, zombie creation rate, human birth rate. Z is represented by ZCR minus ZDR. H will be represented by HBR minus HDR minus ZCR. These are merely the rates and not the amounts. The totals can be represented by zombie deaths, human deaths, not zombie related, zombies created, and humans born. In other words, ZD, HD, ZC, HB. Now we can redefine Z1 and H1 in the following way. Z1 will equal Z0 plus ZZ minus ZD. H1 will be equal to H0 plus HB minus HD minus ZC. As the success condition is when Z1 equals H1, Z0 plus ZC minus ZD equals H0 plus HB minus HD minus ZC. We can work with this equation to get Z0 plus 2ZC minus ZD equals H0 plus HB minus HD. Now that we have a clearer equation with 6 unique terms, we only need to find how to properly define them. If we accept that HB and HD outside of zombie contact are similar enough to cancel out, the equation becomes Z0 plus 2ZC minus ZD equals H0 minus HD. We can take human zombie encounters as our measurement / unit of time. Human zombie encounters can end in the 6 following relevant ways. 1. Nothing happens. 2. The human kills the zombie. 3. The human kills the zombie but is turned. 4. Human kills zombie but is killed. 5. Zombie kills the human. Or 6. Zombie turns human. These 6 outcomes each hold unique effects on the equation. 1. Nothing happens has no unique effects. 2. ZD plus 1. 3. ZD plus 1 and ZC plus 1. 4. ZD plus 1 and HD plus 1. 5. HD plus 1 and 6. ZC plus 1. If we accept these as the only possible outcomes, we can determine how likely each becomes based on a few factors. Zombie speed, zombie vitality, and zombie infectivity. The faster the zombies are, the more likely an encounter will result in a conflict. The stronger they are, the more likely a human is to be killed outright. The higher the infectivity of the zombie virus, the more likely a human is to be killed/turned. We can grade each of these on a scale between 0 to 2, with 1 representing a human's assumed general effectiveness in each category. The 6 outcomes are affected in the following way. Nothing happens, more likely with lower speed, stronger zombies, and lower infectivity. Human killing zombie, more likely with lower speed, weaker zombies, and lower infectivity. Human kills zombie but is turned, more likely with lower speed, weaker zombies, and higher infectivity. Human kills zombie but is killed, more likely with higher speed, weaker zombies, and lower infectivity. Zombie kills human, more likely with higher speed, stronger zombies, and lower infectivity. Zombie turns human, more likely with higher speed, stronger zombies, and higher infectivity. Put simply, if we can determine the outcome with the highest odds, we can likely use that to determine the odds of a successful outbreak overall. The 6 formulas, they all need to add up to 100%. So regarding all the terms, there will be 3 with lower speed, 3 with higher speed, 3 with stronger zombies, 3 with weaker zombies, 4 with lower infectivity, and 2 with higher. That totals 18 criterion, with 1 over 18 equals 5.556%. Therefore, if every value was 1 on the 0 to 2 scale, each outcome should have 3 or 1 over 6 chance, equaling a 16.667% chance. This is represented by a 1 over 18 3 times over for each outcome. As an example, with zombie speed at 1.5, zombie vitality at 2, and zombie infectivity at 1.2, their negative counterparts being 0.5, 0, and 0.8, they should all add up to 100. Because there are more low values for infectivity, they don't follow a simple rule, as 3x plus 3y equaling 6, where we can see 3x plus y equals 6, or 2 equals x plus y. Instead, 4x plus 2y equals 6. So 2x plus y equals 3, and y equals 3 minus 2x. So if x, the smaller value, equals 0.1, y is actually 2.8. So since in our example x is 0.8, the larger value y must be 1.4 and not the 1.2 as decided earlier. This all totals 18 out of 18 as expected. So in this scenario, the following outcomes have these probabilities and effects. 1. Nothing happens, 18.3% of all encounters. Or 2. Human kills zombie, 7.2% of all encounters, the effect being ZD plus 1. Or 3. Human kills zombie but is turned, 10.6% chance, zombie death plus 1, zombie created plus 1. Human kills zombie but is killed, 12.8% chance, zombie death plus 1, human death plus 1. Zombie kills human, 23.9% chance, human death plus 1. Zombie turns human, 27.2% chance, zombie created plus 1. Again, our equation is Z0 plus 2ZC minus ZD equals H0 minus HD. Let's conceptualize this E0 with a smaller H0 of 50. Our Z0 will be 1, or the patient 0. How many potential notable outcomes are there? One guess would be H1 equals 25. However, this isn't necessarily the case if we look at alternating between 2 and 6. 2 being human kills zombie, and 6 being zombie turns human, which would make the lowest possible amount 98. Therefore, the maximum is actually 2 times H0 minus 2. With the maximum being 98, we can compare to the amount of encounters needed for a successful zombie outbreak. Let's solve for x, with x being the number of encounters required. After entering in the relevant percentages for each outcome in the following equation, we can solve for x, or encounters, to be roughly 60. Since 60 is less than 98, this zombie outbreak in particular is successful. For an unsuccessful zombie outbreak, let's look at some different numbers. As an example, with zombie speed at 0.8, zombie vitality at 1, and zombie infectivity at 0.7, their negative counterparts would be 1.2, 1, and 1.3. Because there are more low values for infectivity, they don't follow as simple a rule. So once again, the larger y value must be 0.4 and not 0.7. The 6 outcomes are affected in this similar way. They total 18 out of 18 as expected. So in the scenario, the following outcomes will have these probabilities and effects. 1. Nothing happens 19.4% of the time. Human kills zombie 19.4% of the time. Human kills zombie but is turned 14.4%. Outcome 4, 17.2%. Outcome 5, 17.2%. And outcome 6, 12.2% of the time. Putting those numbers back into the equation and using 98 still as our maximum number of encounters, we get x to be 133.87, which is too many encounters, and therefore the zombie apocalypse under these conditions is determined to be unsuccessful. So ultimately all we need to do is to compare x to 2 times h0 minus 2. Let's see if we can find a quick solution. We can replace the numbers for our outcomes with variables where a equals 2 minus d, b equals 2 minus e, and f equals 3 minus 2c. Alternatively, 2 equals a plus d, 2 equals b plus e, and 3 equals f plus 2c. Using 2 times h0 minus 2 as our maximum number of encounters with a notable outcome, we can determine x to equal h0 minus z0 over 6 plus 3f minus 4e plus 3d over 18%. Therefore, all we need to determine are the values for h0, z0, d, e, and f, or if we wanted to flip it, a, b, or c, with d marking the zombie's speed, e marking the counterpart to zombie's vitality, and f marking the zombie's infectivity. To flip e to b in our equation, we would use the equation of 2 equals b plus e, rearrange that to e equals 2 minus b, and take the original minus 4e, insert 2 minus b where e is, and get minus 8 plus 4b. The resulting equation will turn out to be x equals h0 minus c0 over minus 2 plus 3f plus 4b plus 3d over 18%. So, for a successful case, h0 minus c0 over minus 2 plus 3f plus 4b plus 3d over 18% would have to be less than or equal to 2 times h0 minus 2. Using some example numbers of h0 equals 7 billion, z0 equals 5, d equals 1.2, b equals 1.8, and f equals 1.7, the resulting calculation is determined that the number of encounters needed is 9,067,357,506.48, which is less than 13,999,999,998, which is the required amount of encounters. Using some other numbers of h0 equals 7 billion, z0 equals 5, d equals 0.2, b equals 0.8, and f equals 1.2, the resulting number of encounters is exceeding the 13,999,999,998 threshold, totaling 23,333,333,316.67. Essentially, in example 1, the zombie virus is successful after 9 billion encounters. Example 2 needs approximately 23 billion encounters, which is not possible as the maximum available before an outcome must be established, success or failure, is about 14 billion encounters. So our equation can alternatively be written as h0 minus c0 over 4v plus 3s plus I minus 2 over 18%, being less than or equal to 2 times h0 minus 2. We can use this equation to calculate any zombie outbreak scenario, including those of popular films or TV shows, where h0 equals the initial human population, z0 equals patient zeros, v equals zombie vitality on a scale of 0 to 2, with 1 being on par with a regular human, S equals the zombie's speed on a scale of 0 to 2, again with 1 being on par with a regular human. I equals the zombie's overall infectivity rated on a scale of 0 to 2, with 0.5 being roughly transmitted solely through bites. With V, S, and I all equal to 2, we can see that the equation will always be a success, as the 2 denominator overrules the plus 1 term. With V, S, and I equal to 0, the equation doesn't quite make sense, so minimums are needed. At least V is greater than 0.5, S equals 0, I equals 0, or V equals 0 as long as I or S is greater than 1.5. Also, the minimum of 0 for each value doesn't make sense, as a zombie outbreak would stand no reasonable chance if the zombies were stationary toothpicks that can't bite. Therefore, our equation has restrictions of V is greater than 0, S is greater than 0, and I is greater than 0, and the summation of V plus S plus I is greater than 0.6, and at least one of V is greater than 0.4, since the others are 0.1 by default, or S or I is greater than 1.4, since we know the other value is at least the other 0.1. Using this equation, we can determine whether or not a zombie outbreak will be successful. Thanks for watching. You didn't even stick with a red marker, you idiot. You're not even wearing the same shirt.